Dear students, I welcome you to Accelerators-Part 3. By the way, this is Dr. Ramchandra working as Head of the Department of Physics, Government College Autonomous, Rajamahendravaram, Andhra Pradesh. Today we are going to learn about linear accelerators. I hope you have been following my lectures regularly. So far, we had two lessons. One is on Cockcroft-Walton accelerator and another is on Van de Graaff electrostatic accelerator. And today's topic is very important topic, that is a linear accelerator, in short form, a Linac. Why it is important? It means it has been using in medical field to treat deadly disease, cancer. And let me go for the details of this topic quickly. So in slides, we have the introduction part and then history of linear accelerators and different kinds of linear accelerators and working principle on phase focusing is very important part of this linear accelerators, and then construction and then application of the linear accelerators. And then now, so linear accelerator is a device that uses high frequency electromagnetic waves to accelerate charged particles such as electrons to high energies through a linear tube. So that means electron trajectories are linear in the accelerator tube, hence the name we call it as linear accelerator. The high energy electron beam itself can be used for treating superficial tumors, and also it can be made strike a target to produce X-rays for treating deep-seated tumors. That is the maximum utilization of this linear accelerators. Okay, so that means we treat the cancer patients by using linear accelerators. And then now let me have a look on the history of linear accelerators. In the late 1940s, the idea of using linear accelerators in the medical application became very interested. So medical linear accelerators have been in clinical use since the early 1950s. So first one was installed in Hammersmith in 1952 with 8 million electron volts. Okay, so let us go for the details of this, how this linear accelerator works and what's the principle behind this. And then, so generally the electrostatic fields which we are using to accelerate the electrons, previously we have seen acceleration by DC voltages like Cockcroft-Walton rectifier generator and Van de Graaff electrostatic accelerator. And then now it is different, that is acceleration by time varying fields. So that means resonant or cyclic acceleration. Of course, betatron is also there. We're going to have this lesson coming days. And then, so this resonant or cyclic accelerations, we have linear accelerators, synchrotron, cyclotron, and RF radio frequency synchrotrons, and then colliders. And then basic types of linear accelerators, we have two, and that we are going to discuss. The one is a Rolf Wideroe linear accelerator and Alvarez Linac accelerator. And let me go quickly about these two and phase focusing condition and the application of linear accelerators today. And then now you can see the acceleration and the energy gain. So the how we are going to accelerate the particles means the general the force is nothing but the rate of change of momentum. So the Lorentz force of a charged particle is equal to the charge means Q or E into the electric field plus the cross product of velocity and magnetic field. Of course, the second term doesn't produce any acceleration. We know we use this second term for bending the charged particle beam. Okay, so it is necessary to have an electric field that's the first, preferably along the direction of the initial momentum. That's the rate of change of momentum is nothing but E into the electric field along z direction. In the relativistic dynamics, the total energy E and the momentum P is linked like this: E square is equal to E naught square plus P square C square. Then if you differentiate this, and then you get dE equal to V into dP. So that means energy gain per unit length of your electric tube, electric acceleration column. So dE by dZ is equal to V into dP by dZ. So that means that is equal to E into Ez. E means charge, Ez means electric field along Z direction. The energy gained, it is nothing but the total kinetic energy gained from the field along the Z path is W, that is equal to the charge into the voltage, applied voltage. This is the general principle, and then now this principle we are going to apply the energy gain. So just look at this here. Then I'm using pointer here. Yeah, so look at this here. Let me go for the pointer here. So just the pointer of highlighter. Yeah. Now, so this is an acceleration gain. So that means a source is there, then electron source here, and then whenever it goes along the two electrodes, so these two electrodes are connected through a potential difference. The first one is a positive and the second one is a negative. The electric field spacing in between these two along the Z direction is Ez. That is a gap. In the gap, the wave which is going to have like this, when the electron beam cross this gap, and then you have gained some energy, that energy delta E, that is a gain energy per electrode, Q into delta V, the potential difference between these two. And this is a general principle. We already seen this kind of principle, and this is simply electrostatic acceleration principle, and then which has been using to accelerate the protons and electrons in case of a Van de Graaff generator. So just see how we applied this principle to this. So that means here source, and then this is the potential difference between the two electrodes, and then the force is equal to E into Q into E, and then the energy gain is nothing but Q into delta V, and this 750 kilovolts of Kirchhoff voltage generated at Fermi's lab, and then this is which we can see, this is the Van de Graaff generator which used at MIT. And this is already we discussed in our previous classes. Now the focus is on radio frequency acceleration. This is very important, and this principle is being used to accelerate the electrons to higher energies by using linear accelerator, Linac. In short form, it is Linac. Okay, so that means electrostatic acceleration limited by simply isolation possibilities. So then that is use of radio frequency fields. So just this is Wideroe type structure. I can tell you about here one point about Wideroe. The first working linear accelerator was built by Adolphe Wideroe in 1928. It used only 3 coaxial cylinders, like here, 3 coaxial cylinders electrodes, and could accelerate the potassium and sodium ions to twice the energy available for a single transversal of the field. So that is the greatness of this Wideroe type structure. And you just see here the cylindrical electrodes, that means drift tubes separated by a gaps here gaps, here to here gap, and here this is a gap, and here gap, and which fed by a radio frequency generator as shown in figure here, a radio frequency generator V naught V radio frequency equal to V sine omega t. And led to alternating electric polarity. So that means this is a positive, and here it is a negative, and this is a positive and the negative, like that. So when the wave is passing through this, then a standing wave is passing through this, the electron gets acceleration. Then we can go details of these linear accelerators by utilizing this radio frequency acceleration principle. Yes. Let me go for the basics of these linear accelerators. So proposed by Ising 1925 and first built, already I told you that by Wideroe 1925. It is just simply the principle is replacing static fields by time varying periodic fields by only exposing the bunch to the waves at certain sections parts. So here it is alternating field where they are applying. And then in this consequences, so the basic idea is the particles, the particles are accelerated by the electric field in the gap between electrodes connected, alternating the poles of AC generator. Now here, yes, you can see here the poles will be connected alternatively here, and the original idea is already I told you this Ising, and then it was implemented by Wideroe 1928, and who applied a sine wave voltage, a sequence of drift tubes like here. So that means here like this, and then you have a sine tube like this. Okay, so that means here the traveling that means these do not, whenever the particles are traveling inside the tube, they do not experience any kind of field, and whenever it crosses the gaps it accelerates. So that's why we call them these drift tube Liinac accelerators. If the length of the tube increases with the particle velocity during the acceleration such that the time flight is kept constant as usual, and which is equal to the half time period of the radio frequency. Yes, the particle is subjected to a spontaneous acceleration voltage. So that means here it is the length of the tube is L, and then L which can be equal to the T by 2 of its voltage. Yes, so we can explain this principle accurately in next slide. Yeah, so you just look at this. When we consider the drift tube Liinac structure with injected a particle with an energy E in initial energy, and then we have different gaps are there. They are arranged coaxially cylindrical drift tubes here, and then the energy gained by this is equal to the, suppose if you keep n n drift tubes, n into q into the acceleration voltage. So here it is. So when you are looking at that means here delta v we are applying the potential difference in between the gaps, and then V RF into cos omega t. So here it is a plus and minus, and then this plus is going to be connected here the first drift tube, and this minus is going to be connected to the second drift tube, and then the next one again the positive, and here the next is a negative, like that. So alternatively they are connected, and whenever this the RF radio frequency which is passed through this, and it has one gap, and which is going to be here like this, and which is going to be here like this, and like that. So this is positive and negative, and suppose if you look at this is a negative and it's positive, and then each and every gap, so that means this is a gap, and which is going to be have like this, and here like this, and each and every gap you have some acceleration. So that means here the energy gained by this particle C for each and every gap, whenever it reaches, then it's going to be up and up and up. So that means the time is equal to length by velocity. So T or F is equal to ln divided by VRF. Suppose if it is the t equal to t by 2, and then therefore you have here the ln equal to half into beta into c into tn. So that means you know the v equal to velocity of a particle, the velocity, and the relation between the velocity and velocity of light, velocity of your particle and velocity of light, and v by c is equal to beta. So according to that, L of n is equal to half beta into lambda. Lambda means it is a wavelength of your sinusoidal wave. So that means the energy gain per unit length, so average acceleration gradient, dE by dl is equal to q divided by v acceleration divided by ln, that tq v lambda into v beta according to this ln equal to half. This formula if you substitute here, so this is the energy gain per unit length of your drift tube length. This is a complete picture of field synchronization condition of a drift tube length. So let us go for the linear acceleration, how it works. So this one is the linear accelerators, or simply I already told you how the construction is here. The linear accelerators, the the charged particle receives the several small energy kicks in acceleration gaps between drift tubes that are powered by radio frequency voltage source. Here radio frequency voltage source. So the L equal to, see, the L equal to V divided by 2F. Sometimes we can write like this also. And then the length of the drift tubes is so adjusted, the time taken by the particle to traverse the drift tube is integral multiplier of half period. Integral multiplier of half period. How many number of tubes you are putting, and then that is integral multiplier of that. And then the drift tube length is the particle velocity depend and increase with the particle velocity. The length is also increases with the increasing the particle velocity. That means by using this principle, the scientists can achieve high energies through multiple acceleration. So that is nearly 55 giga electron volts and then 250 giga electron volts, like this. And then the next type of accelerators are resonant RF cavities. So like this, so in previous Wideroe developed accelerators, there would be a small problem. So that is, suppose if you the particles get high velocities through the drift spaces and get longer and loses its efficiency. So that means we need to, the solution for this is we need to increase higher operating frequencies. So, and one more thing is, so when due to circulating currents developed on the electrodes, it is proportionally to the radio frequency. We have to increase the radio frequency. That is only one thing when you adopt the procedure of Wideroe Liinac accelerators. But the solution for this is to enclose this system in a cavity. The resonant frequency matches the RF generator frequency, and then you can generate, you can give the, we can accelerate high energies of electrons. So let me take the next cavity type Linacs here. So these devices store large amounts of energy at a specific frequency, allowing low power sources to reach high fields. That means here you can observe here very clearly. So here radio frequency amplifier is there, and then splitter is there here. So its splitter goes, so each and every one which acts as one cavity type. So here when the particle velocity, the phase velocity of this field, which is equal to the particle velocity, and the resonance occurs, and it goes to generate higher acceleration, and then you gain higher energies. Okay, so then here this is the principle of Alvarez. You can see here the Wideroe structure becomes insufficient at higher frequencies due to dissipation of electromagnetic energy. But here Wideroe Alvarez structure is enclosed in a metallic tank to form a resonant cavity. Here it is, you can see here very nicely. So that means the Alvarez at the University of California, Berkeley, built a proton linear accelerator using 47 drift tubes at an radio frequency, RF frequency of 2.5 megahertz. The protons were initially accelerated to 4 million electron volts by Van de Graaff accelerator, and then injected into the first drift tube here and to the accelerator. The final energy of the proton whenever it comes out, so 32 million electron volts. The drift tubes are housed within a 40-foot long vacuum chamber of diameter 4 foot, which acted as a resonance cavities. So these are the resonant cavities. By that they produced, that means Alvarez produced 32 million electron holes. Initially the electrons were injected through protons were injected to Van de Graaff generator. So this is the working principle of Alvarez. Then let me focus the next concept of phase focusing. So phase focusing means generally the RF acceleration means E equal to Ez into sine omega RF into T. So that means this is energy gain. Energy gain is equal to EV into sine phi. That is phi means, sine phi means phase. The phase is also important point here. So that means to focus the phase whenever it going from one electrode to another electrode. So generally the common phase conventions are for circular accelerators, then origin of time is taken at zero crossing like here. And whereas in case of linear focusing, for suppose here we started the positive crest here, the positive crest RF voltage. So that means here E naught into sine omega RFT and E cos omega RFT. Here it is the sine 1 and here it is cos 1. You just see. And then now, so let me stick to the first one, and then the phase stability condition is, let us consider a success of acceleration gaps operating in a 2 pi mode, and I will show you later the 2 pi mode or pi by 2, 3 pi by 2 and 0, these modes, how this phase focusing, and which is synchronized condition and fulfill the for phase 5. And this EVS, so that means the energy, the charge into voltage, stable voltage, and EV into sine phi s is the energy gain in one gap for the particle to reach the next gap in the same RF phase, So let us consider here there are some points P1 and P2 and N1 and M1, and here M2 and N2. Now here it is M1 and N1. And first suppose if the energy increases is transferred into a velocity increases. Okay, so M1 and M2 will move towards the P1 is a stable one, and whereas M2 and N2 they move away from the P2, that is unstable. So that means, so it is a stable condition means they move towards the P1 and here it is unstable. The energy is increases into the velocity is automatically increases. This is the condition. And then now how the phase relation is important when between the gaps. It just, you can see the modes and the phase differences between the adjacent cells. If you can see different modes 0, 2 pi, pi by 2, 2 pi by 3 and 5. And here it is, the cavities are there. Suppose if you take 0, 2 pi phase beta into lambda, and here pi by 2 phase, how this phase focusing, and then this one is 3 pi by 2 pi by 3, and this one is 5. And then now, so these are the different phase focusing and some multi-cell cavities. So when you are looking at this, and then disk loaded traveling structure, so that means the idea is suppressing drift tubes long, then a continuous acceleration, the phase velocity of the wave needs to be adjusted to the particle velocity. So this is the thing which you have to learn from the phase focusing point. When you are looking at this traverse focusing fields at the entrance and defocusing at the existing the cavity. So at the entrance focusing fields focused, and that existing it has to be defocusing. And then in electrostatic case, so energy gains inside the cavity leads to the focusing point. In RF case, radio frequency case, field increases during the passage. So that is a transverse defocusing. That means longitudinal phase stability means dou v by dou t, the rate of change with the potential is greater than equal to 0, and that implies the electric field along z direction is less than 0. So that is a defocusing. It is a focusing condition, and the defocusing is dou Ez by dou x is greater than 0. So this is the phase stability condition. By utilizing whenever this particular the phase velocity is equal to the particle velocity, then resonance occurs, and along entire the tube whenever we opted the resonance cavity in a vacuum tube. So these principles utilize, by utilizing these phase conditions and phase stability, the scientists have developed linear accelerators, different kinds, and this application is very important for this linear accelerator, that is medical linear accelerators. I want to go this for this medical linear accelerators very quickly, and then now, so here the use of this linear accelerator accelerators means here you can see directly here. So that means Henry Kaplan MD. So he worked with a physicist Mitchell Wisbloch to apply this radiation on a patient. So that means this treatment, the first patient of this linear accelerator is a 2-year-old boy. So this first patient who is 2-year-old boy who received the radiation therapy from the medical linear accelerator at Stanford to treat his eyesight actually. So he lived rest of his life with his vision very intact. Okay, so that means, so let me go for the basic principle of this linear accelerator to use in medical linear accelerators. So you know that this is an electron source. We need a source. So that means it consists of cylindrical shape electrodes like here, cylindrical electrodes and increasing length arranged in figure like enclosed in a glass vacuum chamber. Alternative cylinders are connected together odd and even to different terminals. Ions from the source kept at one end and move along the axis of the tubes and are accelerated on crossing the gaps between the tubes. And then ions are not affected inside the tubes because we know the principles. Already we learned mathematical formulas for this, and the potential is there constant. And then if ions are positively charged and moving from the left to right, if a first cylinder is positive and second cylinder is negative, and then ions are accelerated to travel the second cylinder with a velocity constant and but greater than the velocity of the first cylinder, and the second cylinder is long enough so that when the ions reach the gap between the second to third cylinder, the potential are reversed. So like that it goes on, the velocity increased ions gain in the gaps between the second and third and fourth, like that. So then you can get higher and higher energies whenever it crosses the gaps. So then this is generally block diagram of medical Liinac accelerator. Electric gun is there, and then here you have power supply, and klystron is there, or magnetron. And then I can say in one word what is use of all this. This is an accelerator tube. We treated these patients, and then we need to make bending of this beam to expose the tumors on a patient tumors. And then these are the basic components. If you can see, these are all the components, and this is the structure, actually schematic structure of medical linear accelerators. There are 6 classes. Injecting column is there. Injection is required for to run the accelerator, and then RF power generator, accelerating waveguide, auxiliary system is needed, beam transport system is needed, and then beam collimination and monitoring system is also needed. And let me go quickly about the injection system. The injection system is the source of electrons. You know, the electron gun coated contain a heated film cathode and a peripheral ground anode, and electrons are thermoionically emitted from the heated cathode and focused into tensile beam in a curved focusing electrode, and the electrostatic field used to accelerate the electron are supplied directly from the pulsar modulator. And once these electrons are come from, and then they are going into the radio frequency power generator system, and then the microwave radiation we need to accelerate the waveguide, to accelerate the electrons in the desired kinetic energy. So that means that is the use of radio frequency power generator system, and it has pulse modulator and RF power source, and then here magnetron is also there, which is a device to produce the microwaves. That means it needs to have radio frequency, and it is a cylindrical construction having a central cathode and outer anode, and space between the anode and cathode is evacuated, and this is simply magnetron is to produce the microwaves. And then clusterons are the microwave amplifiers. So that means the electron produced by the cathode are accelerated by a negative pulse, and which can taken up to the higher energies. So then the next one is accelerating structure, and it consists of copper tube. Already we have learned how it works in previous slides, and like that whenever it comes out, the accelerated beam comes out of this, and we need to focus on a particular target. So that means, so which is, there are some electron beam transport systems are there. So once if it comes out, and then we need to bend that accelerated energies of electrons. So that means here 90 degrees bending and 270 degrees bendings are there, and then this bending magnet. So this bending magnets systems, they are like this. So that means the bending is possible through magnets only. So 90 degrees bending and 270 degrees bending and 2.5 bending. So different bending setups are there. This bending setup is highly essential to focus this particular accelerated beam on a target. Okay, and the Linac head is also there. Here some electron beam comes and it goes to the preliminary collimator, and then secondary collimator, and then wedges and different parts of Linac head you can see in the figure. And then finally, so this is the diagram. A and B. This A is the photon beam which can fall on a patient. Like whenever it comes, the electron beam strikes the X-rays, and then whenever it comes to the primary collimator, and then ionization chamber is here, and then finally it comes. So here it is a photon beam which treat the patients, and then electron beam is also we use to treat the patients and tumors. And then like this is the setup they are using in medical Linear accelerators to get the electron beam. So here also primary collimator, and then secondary collimator, ionization chamber, and some secondary collimator, many parts are there. And then if you want, you can learn all these things. And then these energies from Linear accelerators are photon energies, 6 million volts, and then here 18 MeV and 8 MeV, and 6, 9, 12 MeV, million electron volts, and 18 million electron volts. This is the electron beam. So different kinds of energies of Linac we can produce to treat the cancer patients. And then now the advantage of this, already I told you this, we basically use this linear accelerators to treat the cancer patients. And not only for that, so particles are able to reach the high energies without need of external high voltage. That is one of the advantage. And linear accelerated attack the effect area with higher doses and radiation of than other machines. So these are the advantage of these linear accelerators. And then disadvantage is also there. It's costly, and also it needs the linear accelerators actually for general linear accelerators there it needs high end spaces actually. So that means the scientists developed nearly 4 kilometers of drift tubes initially they developed, and after then resonance cavity principle they used it and they minimized it. And then this is also maintenance is little bit expensive. These are the some disadvantages, and hope you are understood the principle and phase focusing and the other different kinds of linear accelerators. Here are some questions for you. So linear accelerator accelerate the electrons to produce what? So that means you know the answer for this question. And the second question is ionization chamber used in Linac means sealed or unsealed. What is? So I can show, I already shown you in figures, and then you can get the answer from that. And the distance between the surface distance, the target to surface distance between the Linac means I didn't tell this one. This is nearly, it should be 100 centimeters. And then next, the bending system, bending magnets we use it in Linear accelerators, and different kinds of bending we can produce. Then you can know the answer by listening this video. And finally, so hope you understood different kinds of Linear accelerators, how they are working, and then how the scientists have developed these accelerators, and finally it applicable to the cancer patients. So it is very interesting part on linear accelerators. So please wait for the next video lecture, which is on cyclotron, means cyclic accelerators. Thank you.